page 85 of the ebook. And that's going to be page 248 of the textbook. Briefly, we're going to talk about one other form of potential energy. I made allusions to it before, which is this energy called elastic or spring potential energy. Sorry to squeeze that in there. So it's going to be spring. I usually refer to it as spring potential energy. So just like gravitational potential energy, it's going to be PE instead of sub G, it's going to be sub S. And I'm just going to give you the equation that they don't give you in the textbook, but we'll probably use it at some point down the line. So spring potential energy has this equation, PS for spring potential, S for spring. And all forms of energy have units of joules. K is what I call the spring strength, but technically it's the spring constant. So depending on the spring that you have, spring, rubber band, anything that can stretch and compress, we just call it spring, we just generalize it. Every spring or every rubber band or every bowstring for a bow and arrow has its own strength to it. So it's called the spring constant. So that particular string, that particular bow has its own way it can stretch and compress. So spring constant, the units are newtons per meter because it comes from the spring force, which is F equals kx. So you divide force divided by meters, it gets newtons divided by meters, but that's just a brief thing. So spring constant is K. Delta X is, again, displacement. So just a quick example of that. Let's say that I had a mass on a spring and I started off in the middle here, X is equal to 0. And I had like a spring attached to this mass right here in the middle. And then I would stretch it a particular distance and say this is X initial, and then this is X final, which is not equal to 0. Something that could be 5, could be 10, could be 100, doesn't matter, it's not 0. So this distance between this initial position, Xi equals 0, and X final is of course your displacement, okay? You can stretch it if you go to the right. With respect to this picture, it's stretching it. And then if you go backwards to 0, it's compressing it. So if you stretch or compress your spring, the energy within that stretching and compression of the spring is called the spring energy. And it's a function of how strong the spring is, the spring constant, and how far you pull it. But it's a direct, it depends directly on the displacement. So if I put the equation down again, spring energy 1/2 K delta X squared. So this spring energy depends on the displacement. So the further you stretch it, the more spring energy you're gonna have. So you know by intuition, if you've ever pulled something before, you know if you pull it far enough, intuitively, you know it's gonna, rebound very, very hard, very fast, because you're increasing the amount of potential in that spring. So when you let it go, that potential energy becomes kinetic energy and it moves very fast. If you stretch it a little bit, not as fast. Stretch it a whole lot, it's going to be very fast. So it definitely depends on the displacement, how far you stretch it or even compress it. If you have a spring or slinky, whatever it is, you compress it enough, you know that if you let it go, it's going to rebound very far and very, very hard from the state of compression, from its compressed state there. And so that's basically this other form of potential energy is a spring potential energy. we'll be taking a look at that when we get to saving energy here in a moment, that this energy, spring potential energy, as well as gravitational potential energy, as well as kinetic energy, are all forms or all energies that relate to one force. And that particular force is the force due to gravity. We'll be dissecting that here in a moment. But all of those energies are, and the force due to gravity is what is called a conservative force, meaning that the force doesn't change no matter what kind of energy you have in the system. So that's just a little bit. It's another form of potential energy. So that's a spring potential. We know that we have gravitational potential. We've seen this already. And they talk about other forms of energy, chemical energy, thermal energy, but we won't concern ourselves with that for right now. Any questions? Anybody need to see any bit of this? So again, they make an allusion to that on page 85 of the ebook, Changing Forms of Energy, but in particular, this spring energy is alluded to, actually on down the line here.
Mr. Kelly?
That would be on page 254. Page 254 is when they make the quick allusion to spring energy or elastic energy. Yes, Ramiro?
Can you go back to the drawing part?
Right here? Okay.
Yeah, thank you.
Yep. So that's, the only other form of energy that we'll be talking about before we get to the conversation on conservation of energy. All right. Let's now change our slide. And, okay, so let's talk about the next part. We're going to talk about the connection between work, kinetic energy, and specifically gravitational potential energy. And if we're tracking it simultaneously with the ebook, we're going to go to page 86, where it's entitled Lesson 3, Conservation of Energy. We are going to derive the equation for conservation of energy, and then we'll talk about it in the context of what you see here in your text. Okay. All right, in the situation that we're going to have, we're going to, drop an object. Okay. So that's what we have there. So let's say I have an object, ball or rock or whatever, and let's say its initial height is 10 meters. Then this is the ground, the final height being 0. We know already that the potential energy in the system is held between these 2 points. Our 0 point, or our reference point is going to be height is equal to 0. So from this reference point, this 0 point here, we can find the potential energy at 10 meters. So before we actually drop this ball or rock or whatever it is, let's find the potential energies at the initial height and the final height. We can do that very easily. You've been tracking along with the potential energy discussion, gravitational potential energy, but I'm going to, we know it's gravitational, so I'm just going to say the initial potential energy at that initial height, mghi, and I'm just going to give it a mass, let's say 2 kilograms, right? Make that up. Just a little object, rock or something. So 2 kilograms times 9.8, meters per second squared. I'll put all the units in there. And so we can get that potential energy at that point. So that's roughly 200, but let's get it exactly. So 196 joules. That's your starting potential energy. And so now we haven't dropped it yet, but we know that the potential energy at the bottom, going from HI equals 10 to H final equals 0, we know immediately that's going to be 0, because 0 times anything, right? So that's our potential energies between the starting point and the final point. Okay, so now we define what the potential energies are at those 2 points. Let's drop the object. So object dropped, HI equals 10. Go all the way down to final equals 0. In this situation, we notice 2 things. We notice that the force due to gravity, well, it always points down, is going to be in the same direction as the fall or the displacement downward. So when we go downward in the y-axis, it's going to be a negative delta y. So force due to gravity is down, the displacement is down. We know by definition of work, and the force that's doing the work here is gravity. We know that the work that's done by gravity is going to be the force of gravity times the displacement, the distance going down, negative delta y. And it's negative because final is going to be 0 minus 10, so it's going to be negative 10. That's why this is negative. So the work done by gravity is going to be a multiplication of the force due to gravity and the negative displacement, the negative vertical displacement. When you multiply those, that's going to be a positive. So we know that the force due to gravity is going to be F sub g delta y. And we also know that Fg is equal to mg. It's the weight, so force due to gravity is mass times gravity. So we basically get back the potential energy, or the change in potential energy equation, so mg delta y. So anyway, the work done by gravity, Fg delta y. So we'll just put that on the shelf for the moment. We know that that's what's going on as the object is dropped. It's moving downward. Gravity is going to do work, which is force times gravity, force of gravity times delta y. That's going to be a positive quantity. So that's the first thing we notice, that the work by gravity is positive. The second thing we can see, or we can notice, is that even though gravity does positive work, at the same time, the potential energy is going to be negative. How do you know that? Well, we just looked at the first case up top. We saw that the potential energy at this point is going to be 0, and that's the final potential energy, and the initial potential energy is going to be 196. So we can take the difference between these two and we'll see that it's negative. So the change in potential energy, gravitational, is going to be the final potential energy minus the initial potential energy, which is 0 minus 196.